Pleasure for me to introduce our today's speaker, Mostafа Адими. In fact, we work together in Lyon, in the same university, and also in INRIA team. INRIA this is a French institution, which means Institut National de la Recherche en Informatique et Automatique. And during many years, Mostafа was coordinator responsible of our team called Dracula for some strange reason. It's kind of a French type of humor. The idea was that when this team was created, the main topic was related to multi-scale modeling in hematopoiesis. Hematopoiesis, it's blood cell production in bone marrow. This is why our younger colleagues suggested this nice name of the group. But by the way, is it still the same name now, or it will be changed, Mostafа?
No, it will be changed. It's now Musics.
Musics. So French tradition is to, no, not tradition, but rather often the teams are called by some abbreviations, but these abbreviations are chosen in such a way that they form some word, some meaningful word. So Musics, I suppose, it's abbreviation of some letters, but
yes, exactly.
Yeah. Anyway, so Mostafà will present us today his new work about continuous time differential difference models in population dynamics and epidemiology. Please, Mostafà, you can start your presentation.
Okay, thank you very much, Vitaly, and thank you also all of you to be here. I will talk about continuous time differential difference models in population dynamics and epidemiology. In fact, I will start with the simple things to fix ideas. If we consider a population model, let's say some n particles that interact each one with together with this ordinary differential system, and we suppose that there is equilibrium, steady state, that I call V star. And if we add what I will call inactive phase in this model given by W, it's a vector, and nothing happened in this new compartment. There is only movement between the first compartment that I can call active compartment and the new compartment is what I will call inactive phase of this population. Everything happens in the compartment V and nothing in the compartment W. The population only move to this compartment and come back again with rate Q in the first compartment. Here P and Q are matrices, but it's only to fix some ideas. I will consider P and Q diagonal matrices to understand. The idea is what will happen for dynamical point of view for this population if we add this new compartment. Okay, this kind of model can, for example, for cancer cells, if we consider, for example, cell cycle, it can be what we call dormant cells. Let's say during the cell cycle, you have many steps before each cell divides that we call G0, G1, S, etc. G0 is what we call also resting phase. Each cell can enter this resting phase and don't divide. You have also for some animals hibernation, or it can be active period for predators. For if we consider a model of predator-prey model, or refuge for prey, or it can be also for epidemic models, immune period, vaccination for, let's say, vaccination with limited period of immunity, or taking some drugs that protect individuals against an epidemic. Many models can have this, what I call inactive phase or slow phase. Many things can happen. This kind of models was studied especially by Hadler since 2008. It was applied for predator-prey, for tumor growth by Gillenberg also and Webb, for cell division with Michael Mackey since 1978, and also for many epidemic models by Hadler and Locher, especially a paper in 2012. Okay, and all these models, let's say they can have some kind of the same kind of model that can apply to this kind of model if you consider, of course, ordinary differential system. How the dynamics change if we add an inactive phase, and can we make like a kind of theory for this kind of model? I will use again this ordinary differential system. We consider an equilibrium V star for the system without inactive phase, and we can see here that the equilibrium for the system with inactive phase is the same equilibrium. There is only a new component that we call W star, because if f of V star equals to 0, you put it in the model, you will have the same component V star that will be the first component of the equilibrium of the system, and the other component is given by W star. Of course, here we suppose that the matrix Q is invertible to have a unique steady state depending on the component V star. Again, to fix ideas, I suppose here that the matrices P and Q are diagonal matrices, and with the same coefficient. It's only to understand the model. Of course, we can make a generalization and consider it's more complicated, but we can consider a general matrix P and Q with Q invertible. Here also we suppose that the coefficient is the same P and Q for each matrix and are positive. How the dynamics will change by adding this a new compartment that is here inactive phase. Okay, we have this steady state. If we consider the Jacobian matrix of the system without the inactive phase, the derivative of V at this equilibrium, and if we make linearization of the system with inactive phase, we obtain this linear system. And you can see that the system has this form. Hadler proved in 2008 that for each eigenvalue mu of the matrix A without active phase, for each eigenvalue for general system, even if the matrix A is of dimension n, that there are two eigenvalues, lambda 1 and lambda 2, associated to mu of the system with inactive phase, and these two eigenvalues, lambda 1 and lambda 2, are given by this this characteristic equation. And you have mu is here. For each mu, you have two eigenvalues. Of course, this is an easy system to solve and to understand what will happen for the new two eigenvalues of the system with inactive phase that depend on the eigenvalue mu coming from the matrix A. And we have this result that was proved by Hadler in 2008. If mu is given by this complex representation, if mu is the eigenvalue of the matrix A without inactive phase, then lambda 1 and lambda 2 has this property. If we suppose that the real part of lambda 2 is less than the real part of lambda 1, in always we have the real part of the smaller eigenvalue is negative, even if the real part of mu is positive. And the other eigenvalue has this property. I put only because this is, of course, you have many others property, but I consider only these two. If the eigenvalue mu is real, then lambda 1 and lambda 2 are also real. And if mu is negative, they are also negative. And if mu is real and positive, you have lambda 2 is negative. That was put it here. But you have lambda 1 is positive, but smaller than the eigenvalue mu. We have, if mu is real, we have saddle point. But the most important case is this one. If mu is complex with beta, the imaginary part, beta different from 0. And it, in the case if mu is a purely imaginary eigenvalue of A, then real part of lambda 1 will be negative. That means introducing inactive phase take off the oscillations, take off periodic solution of the system. And in the case if alpha is positive, and if beta, the imaginary part of this eigenvalue is big enough, then we have also stability of the system with inactive phase. The conclusion, we have many other properties that I don't put here. Also, in the case when alpha is negative, we have a more stable system, if we can say this. The conclusion is a stable steady state stays stable. That means introducing inactive phase doesn't destabilize the system. And if we have an unstable steady state, this may become stable depending on the imaginary part of mu. If the imaginary part is big enough, we can have the inactive phase can stabilize the system. And for eigenvalue that with large imaginary part beta, the inactive phase moves the new eigenvalues to the negative real part. This for ordinary differential system, and this is the motivation of my presentation. Of course, we can Hadler and other authors make other kind of system, not exactly inactive phase, but let's say a phase with a slower dynamics. For example, if you take here the same nonlinear function f for the first phase, the first compartment of V, and you put a new compartment, you multiply this nonlinear function by kappa, a coefficient that is between 0 and 1. And if you put also the movement between these two compartments, you can also study this kind of system and make stabilization of the system by adding this new compartment. Of course, we have also many studies about when the coefficient P and Q depends on V and W. That means if the rates are depending on density, we have other studies that generalized the system that was introduced by Hadler in 2008. And also, if we consider, this was only a remark from Hadler, Helen, and Lovis in 2008. If the first system is with delay, and if we put the same kind of, we add an inactive compartment with the constant movement between the first one and second one, we don't obtain the same results that was obtained for ordinary differential system. And for example, if we take the system with delay without inactive phase, you have an infinite number of steady state, and they were not able to link the new eigenvalue of the system with inactive phase to the eigenvalue of the system with delay. This is still open problem in a general case. Okay, we can also add inactive phases for, let's say, partial differential equation, for example, for age structured models. Here, I consider a very simple model. Let's say we have a population that can be in two different compartments. The first one is active compartment, because you have here, let's say, mortality, you have the production that's given by alpha in terms of the total population V of t, and we add a new compartment that is, we can say, inactive compartment, because there is nothing happens here. There is no production, no mortality, and no a newborn. And we want to see, this is, my question is about what is the difference between this kind of model in comparison with the ordinary differential system. The thing important here is the duration of this compartment. If we suppose that the duration is tau, tau will have impact of the system. And you have also here the same, the movement from the active compartment to the inactive compartment is given by the matrix P. And here we take A is the age, is the time spent for in each compartment. It's not necessary here. We suppose that the age go from 0 to infinity, but we can make a limitation. It's not a problem. And Q is the movement. Here we have Q and identity moins Q. That means a part of, at the end of this phase, when A is equal tau, a part of this population come back in the same compartment, and the other part go to W. Identity moins Q. They stay in the same compartment, and this one go to the compartment V and start again a process. This can be like population for vaccination. These people update their vaccine and stay protected, and the other one don't update their vaccine and go to, let's say, susceptible population, if we suppose here that V is susceptible and W is vaccine population. If we suppose that the matrix P and Q are diagonal matrices, we can integrate this first equation over the age, and we can use the boundary conditions, and we obtain this differential equation. Here it's the derivative of capital V of t if we integrate, and we suppose that V of t plus infinity is equal to 0, then you have V of t 0. And this V of t 0 is alpha of V plus Q of WT tau, with Q given by this expression. Then you have this blue part. And the other, this equation can be also solved by method of characteristics. As nothing happens here, it's only the population at time t at the end of this compartment. That means when the age is tau, it's only the population that enter at age 0 and stay until time t minus tau, because you make the difference. Here we suppose we take the case when t is bigger than tau. If t is less than tau, we use the initial condition, but I am not interested here, as we are interested in the asymptotic behavior. I suppose that the time is big enough. And
excuse me, Mostafá, if I can ask a
yes,
short question to better understand. In the first equation, the first line, so you have this minus PV, and this is for any age, right? But then,
yes.
Yes, but then but then when they go to this another compartment, they start with age 0, right?
Exactly.
So they can leave the first compartment for any age, but
yes,
they go to the second compartment and they start with 0 age.
Exactly, because the age here and here, they are different. Each time that we start from 0, it's not a real age, it's age in the compartment.
Yeah. Okay. So the motion from the first compartment to the second compartment, it's like you start from 0, right?
Exactly. As also here, you start also from 0.
For example, in your example with vaccination, for example, if somebody has vaccination, so he moves to another compartment and starts from time after vaccination, from time 0 after vaccination, right?
Exactly. For example, if the vaccine stay like 3 months, let's say, it will be between 0 and 3 months, and after that, and A is between 0. One age equals to 0 for vaccine, for example, is the day that he take his vaccine. And at the end, for example, after 3 months, if he updates his vaccine, it starts again from 0.
Okay, thank you.
Yeah, you're welcome. Okay, if we put, in fact, what I will do here, I will reduce this simple system to ordinary differential system, if I can, or delay differential system, in terms of capital V of t and capital W of t. But I will not take into account capital W of t, because this is very easy to compute. I will consider only the new population that starts at time t with the age 0. This is why here I put U of t is W of t 0. And the nonlinear part, F of v, I put this one. Then if you see the system here, if we use this expression, here you have a W of t minus tau. That means it depends only on W of t 0 or W of t minus tau 0. And you obtain this, this new system. The system can be reduced to this one. And this is like kind of hybrid system, because you have, ordinary differential system and difference one. And this is like we mix between two kind of models. This is a difference system with delay, and if we take, for example, here q prime here is only the parameter 1 minus q. If we suppose that we can consider this like implicit delay differential system. The delay is implicit because it's given by this difference system. If we suppose that tau equals to 0, there is no period of inactive phase. If you take tau equals to 0 here, you move u of t in the other part. As q is equal to 0, q prime will be 1. And if you put it here, you will have, as tau is equal to 0, q prime will be 1 minus q. You put it here, you will obtain u of t equals p of v of t. And you put it here, and this will cancel. In that case, you obtain only the active phase. And this is normal because if we take off the inactive phase, we obtain only the active one. It's only to make a difference between the first model that I consider ordinary differential one and this one. What make inactive phase happens is tau. If tau equals to 0, you will have only active phase and not inactive phase. And also the steady state are the same for this system. The steady state of this system is V star P over Q V star with f of V star equals to 0. If we try to do the same as I did for ordinary differential equation, if we take the Jacobian matrix, associate to this ordinary differential system, then we can prove the same result as Hadler for each eigenvalue mu of A. But here it's not only, we will not find only two eigenvalues, but a family of infinite number of eigenvalue given by this characteristic equation, because it's a transcendental equation. For each mu, you have a countable number of eigenvalue. And even if mu is real, we can have a complex eigenvalue. And this is what is new in comparison with the model of Hadler. And the question is, can we make a stabilization of the system? And this is the hard part. Because the only result, because as this is complicated, and I will show you that we can have some eigenvalue that come from infinity and come directly to the part of complex plane for a positive real part. Okay, consider the case q equals to 1. Q equals to 1, that means q prime equals to 0. And let's see what happens if you take q equals to 1. That means our system, because if you take here q equals to 1, q prime will be 0, and u of t, you can put it here, and you will have direct u of t will be p v of t, and you put it here, and you will have a delay here. You obtain this delay differential equation. And let's try to compute the eigenvalue associated to this delay differential system, associated to the eigenvalue mu of the matrix, the Jacobian matrix of the function f. The associate characteristic equation is given by this expression. And if I will suppose here that mu, we have periodic solution. That means mu is given by this purely imaginary root plus minus I beta. This is only to avoid some singularities. Then we prove that the real part of lambda is always negative, even if we have, that means here also inactive phase strongly stabilizes the system because of the duration of this phase. But of course, the delay in general creates oscillations, and we will see that it's not always the case here because we consider real inactive phase. If we take here even slow active phase, we can have some Hopf bifurcation and periodic oscillations related to the delay tau. I will, this is one example that we already considered in our team, is about the cell cycle. The cell cycle is a sequence of events that take place in cells that leads to division. You have two phases, what we call proliferating phase, and we have a quiescent phase, which is for us what I will call inactive phase. And proliferating phase is active phase. During the active phase, each cell divides and gives two daughter cells. A part of them enter quiescent phase, and the other part stay in the cell cycle to divide again. Schematic representation of this cell cycle is given by this figure. This is the active phase, and this is the inactive phase. At the end of this active phase, that the duration is tau, a part go to the inactive phase, the resting phase, and the other part come back to the active phase to divide again. And the model that can be used to model this, the proliferation of cells here is this one. This is a quiescent phase, this is mortality, and this is the cells that enter to the proliferating phase to divide again. And during this phase, here I told you that we can consider quiescent phase with limited duration or with infinite duration, and we can consider proliferating phase with, this is another kind of models. The only thing is you have active phase and inactive phase. And the flux between the two phases are given by this boundary condition. This is the new resting cells that enter resting phase after division that come from the end of the proliferating phase with age equal tau. And this is the new proliferating phase. You have the one that comes from resting phase and the one that come back with the rate k to divide again. The number 2 is for division. We do the same by integrating the system over the age and using the same technique that I showed you before. We can write the system as this differential difference system, continuous time differential difference system. Here it's only to show you that this kind of system can create oscillations. If we consider there is two steady states, 0 is a steady state that always exists, and you have a positive steady state that exists under some conditions. The function beta here, the nonlinear function, is a decreasing Hill function. And I will show you only by numerical simulations, but we can make analytic investigation. This part is the part when the positive steady state exists, and the other part there is only trivial steady state. And if we we increase this parameter. Beta 0 is this coefficient, and delta is the mortality rate in the resting phase. If we increase mu, a zone of instability, area of instability appears suddenly like this. The axis here is the duration of the cell cycle, and the axis here is the parameter kappa is the parameter k, which is the rate of for cells to stay in the resting phase. And this area, if we continue to increase the parameter mu, this area of instability increases and for positive steady state and becomes like this. And if we continue to increase very high, it will stay like a zone of instability like this. And if we can prove this by moving tau from 0, and we prove that there is a Hopf bifurcation here, we can do it also with the parameter k or with other parameters. This is also to show you that we can have also instability, create instability by putting two phase of one active and one inactive. Can we write this system in general way? This is, we can, this kind of system can be, has this form. Of course, we can have many stages of inactive phase with different time. This is why we can take a finite number of delay. And I put here minus, it's only for application. This is what we can call mortality, and this is the production. You have here mortality, and you have here the production. And the idea how we can study theoretically this kind of system, difference one and differential one. A and BI are matrices. For the existence, uniqueness, and continuous dependence, it can be done in the classical manner. You integrate this and use fixed point theorem. For steady state is a constant solution. We can, if we suppose that this matrix is invertible, for example, if we assume that F is increasing and G is decreasing, we can have a unique steady state, and we can compute one component, and after that the other one given by this expression. There is no problem to define steady state and to investigate existence, uniqueness, and continuous dependence. We can have also linearization by taking the Jacobian matrix of F and G. We have this linear system, and the characteristic equation has this form, where M is the Jacobian matrix and F, and N is the new matrix that is the derivative of G. We can have this in general, this kind of characteristic equation. Now, as you see, until now, I consider only one delay for the model that I show you. Is it we can make generalization if we have many delays? The answer is no, because I have there is some problems to have many delays. One of the main problem is a problem of continuity. I give you here an example. If we take this difference equation with two delay, I forget the other compartment because it's more easy to see it here. If we consider two delays, tau n and 2, tau n is 1 minus 1 over 2n plus 3. We can see that if n go to plus infinity, this go to 1. The solution of this difference equation is given by this expression. We have this solution, and we can see that 0 is unstable, because if you t go to plus infinity, this is the limit is not 0. But if you take n go to plus infinity, you obtain this difference equation, and the characteristic of this equation is given by this one. This is a second order polynomial in the exponential, and we can there is only one root that all the roots, sorry, are given by the real part of all the roots has a negative real part. That means here we have stability and instability. That means we cannot use a method of Hopf bifurcation to increase the delay, because there is problem of continuity for this kind. And the problem is the same if we take differential difference system with 2 delays. Another problem is also we can have some eigenvalues that come from infinity. To explain, let's consider this differential difference system. If we take tau equals to 0 here, we can calculate v of t. It's u of t. You put it here, and you obtain this ordinary differential equation with the u of t is 3 times v of t. Then here we can see that v of t go to 0. That means 0 is asymptotically stable. But if we take tau bigger than 0, the trivial equilibrium is unstable. That means there is, if you take tau equals to 0, you have stability, and for t bigger than 0, it's instability. That means there is a set of eigenvalue that come from infinity and appears in a part of the complex plan with the real part positive. This is there exists another sequence of eigen coming from infinity in the complex half plan on the right, that means with the real part positive. And this is a huge problem because we cannot use, for example, a method of Hopf bifurcation to increase tau from stable from the left to the right to cross the imaginary axis. That means eigenvalue with the real positive part can appear in the half plan on the right and create instability. This is, I have here a proof for this. It's very easy. If you take the characteristic equation, you can write it like this. And as this function is an entire function, that means for each tau, we have infinity different 0. And that means this is property of entire function, the limit of this infinity of roots. The modulus of this eigenvalue is plus infinity. And if we take this limit in the characteristic equation, we can see that lambda n approaches the roots of exponential lambda tau lambda plus 2 equals to 0. And if we solve this equation, you have this solution, and we can see that the real part of this this complex number are positive. That means the eigenvalue of this appears for tau bigger than 0. Of course, there is another branch of eigenvalue that start from 0 and stay negative, with the real part negative, but there is another eigenvalue that comes with the positive real part. Okay, but we have a fundamental result that help. For example, many system has this linearization. If we consider only one delay, and you have this result. That means if alpha here is less than 1, we can use Hopf bifurcation, and there is a continuity for tau from 0 to until near for tau from 0 increasing, but in a neighborhood of 0. If every solution approaches 0, then we have modulus of alpha is less than 1. And also, if the modulus of this parameter is less than 1, every solution for tau equals to 0 approach 0, then there exists a neighborhood of 0 that every solution tend to also to 0. Okay, I was talking about this is for this kind of model. Of course, we can use Hopf bifurcation, and we can construct a characteristic equation. And if we stay with alpha with this condition, we can use the same theory as for the Lie differential system. Here I give also an example of SIR epidemic model with temporary protection phase. You have here susceptible. The age here is the same as I said before. Is the age in this compartment, and the age here is the age in this compartment. And you have here also infected population, and the protection compartment is each individual that enter to this compartment is protected from infection. It's like vaccination, but at the end of this vaccination, some people update their vaccine and stay protected, and the others becomes susceptible again. Here I will go fast. We use the same technique that I used before. You have this, this is susceptible, protected, infected, removed, and this is the people that are start their protection, and this is the end of the protection. And you can see here we can concentrate only on SIU, because SIU is independent on P and R, and after that we can add these two components. Then we stay only with SIU, and we have steady state. This is I will go fast. We have a steady state. The steady state are given by this expression, and we can see that from the last one we have U star given by this expression, and from the second one we have two cases, or A star equals to 0 and we have disease-free steady state, or A star bigger than 0 and we have endemic steady state. And this is given by this expression. This one is the disease-free steady state, and here you have the endemic steady state, and we can compute the basic reproduction number, that is the threshold for the existence of this endemic steady state. If R0 is bigger than 1, we have this positive steady state. And we, as I did before, it's also an example. We can have a system here and only a scalar difference equation. Of course, we can have also here a system of difference equation with many delays, etc. The characteristic of this system for to study the local asymptotic stability of the disease-free steady state is given by this expression. Here we have a real eigenvalue, and here we have transcendental equation, and we prove for the real one depends on R0. This is, I will go fast, and we prove that for this one, all the real part of lambda is negative. That means the stability of the local asymptotic stability of disease-free steady state depend only on R0, and we have these two cases. If R0 is less than 1, the steady state is locally asymptotically stable, and if R0 is bigger than 1, the steady state is unstable because everything is done by this real eigenvalue. For the local stability of the endemic steady state is more complicated because we have a second degree of this transcendental characteristic equation with exponential here. We have also here a second degree, which is very complicated to study. However, if we take tau equals to 0, we can prove that all the eigenvalue have negative real parts. And if we try to see, if we go from 0 and we follow this steady state, if we will cross the imaginary axis, we find that it's not possible. This is done here because we have a polynomial of 4 degree, and we prove that this has this form. We prove that all the solution of this system is complex or negative. That means it's impossible to find W. That means there is no root, purely imaginary roots. But the problem is maybe we will have eigenvalue that comes from infinity. And this is, we also do it, and we prove that all the eigenvalues that come from infinity for this system comes in the negative real part, in the part of the complex plan with negative real part. That means we can, as alpha is less than 1, between 0 and 1, this is a negative. That means as we prove that we cannot cross the imaginary axis, we have also always local asymptotic stability of the endemic steady state when it exists. Okay, this is the proof. Oh, sorry. Yes, I am not in the good, yes. Yes, and thank you very much for your attention.
Yes, thank you very much, Mostapha, for this interesting presentation. It's really a topic which we do not discuss very often, so I think that it was interesting for everybody, for all our listeners to learn more about such kind of problems. So we have some time. We have some time for discussion, and I have the whole list of questions. Are you ready for that?
Sorry? Ah, you're already.
No, I ask you. I am saying that I have many questions.
Yes.
Okay. Show please slide number 10.
Slide number 10. Yes.
Yes, this one. You know, before you considered the case of, or maybe the previous slide, where you have this Q and Q prime.
Yes.
Maybe it's the previous slide, because at some point you had this assumption that Q prime equals 0, and if Q prime, so Q equals 1, Q prime equals 0, and then you reduce these two equations to one equation, yes, shown in the next slide, and then you explained what happened for this one equation, but then you did not return back to this more general case where Q prime is different from 0. So I kind of missed this point. So maybe you can return to that and explain. So again, this system of two equations, not just one equation, but two equations with Q prime different from 0.
Yes, yes. No, I didn't present this. This is, you are right, but I didn't. This is an example that I took to only to show you. No, I didn't study this for in general case.
Because what is shown in the next slide was this q prime equals 0.
Yes.
You explained this equation for lambda, that it moves the eigenvalues to the left half plane from the imaginary part.
Yes.
But in the case of q prime different from 0, it's not necessary so, right? I mean, you don't know.
Yes, I don't know, because in fact, to study for q equals to 1, we cancel this and we have this easy.
Yes.
And if q is not, of course, it's more complicated, and you have to study and to show if there is if we will cross the imaginary axis or not, and if we will move on the right or on the left. Yes, this is.
Yeah, I suppose that it is a natural continuation of this work, and this is interesting to know what happens in this more general case. Okay, let's go forward. Slide number 12, please. Yes, this one, because in the previous model you can see that this this second equation for the resting phase was with 0 in the right hand side, but here you write this minus gamma p, so probably it corresponds to mortality. Yes. In this resting phase. Well, I suppose for gamma 0 you return to the previous model, but for gamma different from 0, what is the difference? Is it basically the same? No, gamma 0, gamma different from 0, or no, this is different?
It's different here. In fact, it's only to show we can, this is the resting phase and this is the proliferating phase, because the production is not only, how to say, during the phase, but at the end of the phase, because
so in fact P, so I did not understand correctly. So yeah. P in fact is not a resting phase. P yes, is exactly. Okay.
It's proliferating phase. You can this is in fact in general what we can say, we have two phases when the behavior are different. What is the impact of each one? This is what we can say in general. It's not necessarily active and inactive, because it depends how you define.
Yes, okay. And capital Q here is this transition between these two compartments, right?
Capital Q is the total population of Q. And this is beta depends on...
this is beta, okay, yes. Beta depends on this. Beta, yes, Q is total population, and beta of Q is this transition between compartments.
Yes, beta is the transition between the resting phase to the proliferating, and it depends on the total population of this phase.
So the method, finally, you show these different models. The main idea is, well, the main approach is similar, that you reduce it to this delay differential equation and then to the difference equation, but in different models, this can be different, right? This, in fact, equations are different. Yeah, but the main approach is the same. Okay, I understand that. So then, when you have these periodic oscillations, I don't remember which slide, but maybe it's a general question. I mean, when the stationary solution is unstable and you have oscillations, is it necessarily periodic oscillations, or you observe also more complex oscillations?
In fact, you can move from stable without oscillations, and when you move, oscillations start, and after that it becomes periodic. Not necessarily periodic, but you can move from without oscillations to some oscillations.
No. Sorry, repeat. To move from stationary solution to what? Repeat. I did not understand.
You can move from without any oscillations to oscillations, or to periodic oscillations.
No. You have a stationary solution.
You have
then it loses its stability, You
Yes.
have periodic oscillations.
Yes.
Then you move like further in the instability region. Can you have more complex oscillations, not periodic but chaotic, for example?
This is yeah, okay. I will. No, this is without. For example, for this kind of model, if you can move here, it's stable. It becomes periodic oscillation. No, chaotic, maybe it's kind of because here we have unbounded solutions. Maybe it's like for a very particular.
Okay, so you in fact in this red region you don't know, it's not necessarily periodic, right? It may
Yes,
be
exactly.
more complex, right?
Yes, more complex, exactly.
Yeah. Well, then there are some questions. I have some questions about this eigenvalues coming from infinity. It's not very simple. I understand it's not a simple situation. Could you show, please, this slide 17? 17.
This one?
No, the previous 17. Yes, this one.
17. Yes.
Yeah,
no,
something like that.
Yes. This
something
is
like that. Yeah.
Problem of continuity, for example.
Problem of continuity.
Yes, if you have this difference equation, and you have here tau, and you make like this is kind of example to show it doesn't work. If you
okay, but you know, if you consider just ordinary differential equations,
yes.
The Cauchy problem for the ordinary differential equations, then this continuity of solution in this classical problem, it always happens. Well, the classical results affirm continuity on a finite time interval. But if you consider an infinite time interval, you may not have continuity of solutions, even for just usual ordinary differential equations.
Yes.
So
I agree. Yes, this is true, because here we give like I don't know how to, because I am very comfortable with delay to see that this is true, because there is equivalence between this kind of model and ordinary differential with infinite.
Yes, and probably also the next slide, 18. Yes. So I missed something about that because here you have only one delay.
Yes, only one delay. But
and you started also with one delay, but then you told us that if you have two delays, it can be a problem because no continuity and because eigenvalues come from infinity. But here again, you have only one delay. So I'm a little bit confused because the number of delays and this problem with infinity.
I will show you what is the real problem, because in fact, is this if you add this coefficient and this one, and if this coefficient is bigger or equal to 1, there is problem. For this kind, of course, a simple one, because here 1/2 it's 1, and the same here you have 2. This is why I give this example. If alpha is less than 1.
Yes. So in fact you can have this problem with this eigenvalues coming from infinity even for one delay, right?
Exactly.
It depends on the coefficient. It depends on the coefficients, like you show in the theorem. I think slide 20. Yes, the next slide. Yes, the next. Yes, this one. So what you prove here, you have just one delay, and all works well if you have alpha less than 1. But if alpha is larger than 1, you can have this problem with eigenvalues coming from infinity, right?
Exactly. When you have many delays, in fact, there is no necessary and sufficient condition. Here we have if alpha is less.
So for one delay you prove that, but if you have two delays, you don't know. You don't have so precise result, right?
Exactly.
So, yeah. Okay. I see.
This is why it's
yes. Yes. Okay. Let's continue. If you are not yet very tired, slide 24, please. it was a little bit rapid, and I could not really. So you see this expression for the basic reproduction number. If we put tau, time delay, equals 0.
Yes.
So no, sorry, this is what I didn't. Yes, okay. I just did not see. Okay. I did not have time to understand the formula. Now, okay, if tau equals 0, you will reduce it to the usual
exactly.
SIR problem, right?
Exactly.
Okay, now I understand.
Yes.
And maybe the last one is slide number 30. I noted it, but I don't remember what is my question. Maybe I will remember if I look at this. Yes, this condition that alpha is less than 1, but I forgot here in this model, in this, epidemic model, what is alpha? Could you show the model, please?
Yes, alpha is, yes, I will show maybe the figure, yes. Alpha is the rate of
okay.
people that
I see.
Only update their...
could you show the model? Probably it's the next slide. So alpha is, yes, in this first, in the first and in the second equation is okay. It's related to this exchange of whether they stay or whether they go away, right? Yes. And here you have this alpha minus 1 minus alpha, so you suppose necessarily that alpha is less than 1, right? Exactly. So your condition that alpha condition in this general theorem is satisfied, or what? Or it is different alpha. No, it's satisfied. It's alpha less than 1. This is true. So the condition of that of the theorem on slide whatever it was 18 probably. Yes. No 20. Slide 20. Slide 20. The conditions of the theorem is satisfied, right? Yes, exactly. For this epidemic. Yes. Okay. I understand. In fact, these are all my questions. Just one more comment is about what I was thinking about during your presentation about these partial differential equations combined with algebraic equations, because you considered as specific type of these differential equations. Of course, there are many others, and I remember many years ago. It was so long ago that I don't remember when, but I studied elliptic equations coupled with algebraic equations. You see, not like hyperbolic equation like in your case, but elliptic equation coupled with algebraic equations. And in fact, it was quite interesting. I think after your talk, I will try to find this old work. I'm not sure that I can find it. It was so long ago that several generations of computers changed. So I'm not sure that I can find it, but I will try. Maybe in view of this work, maybe I have a new point of view on such kind of problems, because indeed in many applications, in particular in reaction diffusion equations, because you might know I work more on reaction diffusion equations. In many cases, there are this exchange terms like you write in your equations, because whenever you have two phases, like for example, if you take like two-phase medium, for example, you write heat equation, right? You have one temperature for one equation and for one phase, another temperature for another phase, and they exchange. Yes. And there are many problems like that. So I don't know. I don't think that there is a general theory about that, but maybe in view of what you are doing, maybe it can be can give new ideas about that. Okay, so summarizing all that, it's an inspiring talk. It was very interesting, new results, new ideas. Thank you very much. It seems to me that there are no other questions. Yes, there is a question from Yana. Yana, please. Yana, yes. Yana, ask your question, please.
I wanted to ask if they have have been any attempts to investigate a similar model of this kind when the inactive phase of is a remission of cancer and the active phase is a relapse? If so, what were the results?
Okay, it's a difficult question. Please, Mostafá, can you say anything about that? Yes.
Because it was not easy to listen. It's about cancer.
About cancer, relapse, remission and relapse. Can you apply such kind of models for remission and relapse of cancer?
Yeah. In fact, no. I don't know, but what I know about this kind of problem, resting and proliferating phase in cancer, that for example, treatment that works only during proliferating phase, during the cell cycle. And dormant cancer cells are one of problem because you cannot, as cells enter this resting phase, are protected against treatment, can make treatment more complicated. Maybe, I don't know, this kind of model can make make the duration of dormant cells as short as possible. Maybe by some kind of to wake up the cells to give a...
Yes, but since treatment, as you explained, since treatment basically acts on actin cells, so you can think about the model where you kill active cells by treatment, but then because you have dormant cells,
Yes, exactly.
You stop treatment, you don't have active cells, but then dormant cells will return to the active phase and will lead to relapse. So the answer to this question asked by Yana, then it might be related. So it's kind of not directly, but such kind of models can be considered. So then we have also another question from Ilya. Ilya, please, you can ask your question. Ilya Ryabtsev.
Good day, you hear me?
Yes, we hear you, yes.
Oh, good day. My question, how do the durations of these phases, whether finite or infinite, affect the dynamics of the system?
Yeah, this is a good question because we can see that it depends, for example, tau, that I consider when you increase tau, you can stabilize or destabilize the system, then it affects the duration of each phase.
No, but the duration tau affects, but the question also was because your age can change in a finite interval, or it can also be infinite interval,
yes,
right?
Infinite.
So what is the difference? Is there a difference between finite and infinite interval for A?
No, it's only, for mathematical point of view, it's more easy to work with infinite, but we can stop it and make or mortality, but it's for theoretical point of view, it doesn't affect the problem.
Right. But the duration of this duration tau of this resting phase is of course important, and in particular, large tau destabilizes, right? If you increase tau, this destabilizes your system, right? As usual in delay models, large time delay destabilizes usually the.
Yes, exactly, in general.
Right. Okay. We have also one more question from Artem Oleinik, please. You can ask a question.
Yes, hello, can you hear me?
Yes, hello, we hear you, yes.
Okay, my question. How do continuous time differential difference models enable the study of the impact of inactive phases on system behavior?
Can you, sorry, because I can't listen very well. You talk about how continuous time? I didn't.
Yes, continuous time differential difference models enable the study of the impact of inactive phases on system behavior.
Yeah, I can.
So let me. Well, I
cannot listen very well.
I understand. Well, I could hear the question, but the exact meaning. I'm trying to understand the exact meaning of this question. So maybe we can reformulate the question. So you have this combination of like differential equation and algebraic equation. How this difference equation, algebraic equation, how it influences the stability. So
yes, I think you're right.
This is
okay, good. I understood the question. It's already.
Thank you.
It's already important.
Yeah,
so you understand the question, right?
Yeah,
so
yes.
how the second equation influences dynamics of solutions?
Yeah, this is exactly what I showed in my presentation. Adding this difference equation can make a stabilization of the steady state for ordinary differential equation.
Yes, but you also explained that it can also destabilize it, right? In some cases. So it depends. It depends.
Yes. It depends on how you choose your phases and how it can stabilize or can also destabilize the system.
Yeah, also on parameters, because I suppose because this eigenvalues coming from infinity. In your case, you showed for this epidemic model that this eigenvalues coming from infinity, they have negative real part. But I suppose that in some other cases you can have positive real parts,
yes,
right?
Exactly.
Yeah.
Many cases can come from appears in this positive real part with positive.
Yeah. I think that we have one more question from Kambulat. Please, you can ask your question.
Thank you. Good afternoon. Can you hear me correctly?
Yes, we hear you.
Okay, Mostafа, I'd like to know how can model parameters be optimized to predict and manage population dynamics and the epidemiological situation? Maybe we can somehow see result by changing parameters of model, looking, for example, on coefficients of birth and deaths.
Yes. Yeah. It's. I think the problem is the same for any other system, not necessarily the one that I present.
Yeah, but the question was about epidemic models. The introduction of this resting phase.
Yeah.
What happens? It reduces
yes.
like this epidemic right outbreaks.
For example, if the duration of this inactive phase, that can be vaccination or protection.
Yeah.
If you increase it, R0 becomes less than 1. You can.
Yeah.
And sometimes it's not very intuitive. It's not R0 cannot be. It depends on the parameter. It cannot be.
But isn't it correct to say that the introduction of this rest and vaccination compartment always decreases R0?
No, it always decreases, but sometimes it's cannot go
beyond. Not necessarily less than 1, right?
Yes, exactly. It can happen. That means for example, one problem was very interesting. It's for vaccination. It's not how many people we have to vaccine, because sometimes it's hard to reach all people, but how many people has to be serious and update their vaccine to.
Yeah. Could you show, by the way, I think we might see this expression for R0, because I see myself on the screen. I prefer to see R0.
Okay. Yes, I can.
Yeah. It was this one. Yeah. Because this term is alpha. Well, you have alpha in the numerator and alpha in the denominator.
Yes.
Which of them is more important? So can we say that this alpha always decreases R0, or this is not necessary?
No, always decrease, of course, R0. If you, the parameter that decrease R0, it's H and tau and alpha. One
Yeah,
tau
but
increase
yeah.
tau, of course, and also if you increase alpha, you can decrease R0. For example, H is the susceptible that you can vaccinate, but if if you cannot, for example, take H as big as you can, you fix H and you play with alpha, because people that are already vaccinated are more how to say, more easy to update than to check for the whole population of susceptible.
Yes, but if you increase alpha, you always can make R0 less than 1.
Yes, exactly.
No, sorry, but
No,
alpha
no.
should be less than 1. Alpha is less than 1, right?
Yes.
So you are limited, not
yes.
Okay, I'm saying you are limited by these conditions that alpha is less than 1. So the maximal decrease if you put alpha less than alpha equal 1, right?
Yes, exactly. Is the maximum.
So still R0 can be larger than 1, right?
Yes.
So, but it's as you say, it's kind of a counterintuitive, because I would think that using vaccination you can always suppress epidemic.
Yes, but you have, of course, you have to play also with H, not only alpha. If you have
H is what in the model? What is H in the model?
H is the people, susceptible people that you vaccinate.
H is I see. Okay, I see that.
Alpha,
Yes,
it's
right,
only
right. Yes,
only
yes, I see.
the
Yes.
update, and the tau is the duration, how
yes, I see that.
of the immunity. Yes.
Okay, Anastasia, please, you have a question.
I suppose I'm the second. The first one with some.
You okay? So with some, you can ask your question.
Okay, thank you. Actually, my question is about this R0, and do we expect oscillations as a solution for this problem?
Sorry, can you
expect what?
Oscillations of
Oscillation.
solutions.
No, there is no oscillations here. It's the system is monotone. Yes.
Yes, because I understand why Wissam asked this question, because we study these epidemic models with immunity waning. So if there is immunity waning, then you can have periodic outbreaks. But here you don't have immunity waning, so you have only one outbreak.
Yes, exactly, because we have this mass action. If you change this, of course, you can have some oscillations.
Yes.
Okay, thank you. Yes, I see.
Please, Anastasia, finally you can ask your question.
Thank you. My question is also about the epidemic model, and it also concerns the model which we consider lastly. You say that inactive phase in the epidemic model, you interpret it as vaccinated people. And can we also model the part of people who are in quarantine?
Yes, exactly.
In the same way, and if not, what is the difference?
Yes, we have also a model with this is a paper that we are working on it now. Is to compare the title is it better to protect susceptible or to vaccinate them? No, sorry. Is it better to vaccinate susceptible or to isolate infected? And we have this, and
I think it will be interesting to read it when it will finally
work that it's
so we can make an appointment for another seminar. So Mostapha, when you finish this work, please tell us. We will be interested, but because we have some not exactly that, but maybe some related works with some other models.
Yes.
We lastly have the problem with how to model the quarantine people, and I thought as I thought before, it is exactly as you presented today. Maybe this way will be
It is somehow related, but the model is different. So this is
yes, but the principle that we should introduce some new compartment which are quarantine people, and it happens nothing in this compartment, but the susceptible go in and go out in some time.
Yes, all right.
But our students think about this. Maybe they choose another way to present this behavior.
I didn't talk also about, because here I consider always discrete delay, but of course we can also make like they can go with probability in any
continuous delay, yes.
and you have a distributed delay and
right. Okay, I think that there are no more questions. Then thank you very much.
Thank you
also for this interesting discussion, and also let us thank our listeners participating in this discussion. We finish our today's seminar. Thanks to everybody. Have a good day. Goodbye.
Thank you very much. Bye.
Thank you very much. Goodbye.
Thank you. Goodbye.
Thank you. Goodbye.
Thank you. Good day.
Thank you. Goodbye.